Section 3.8 is kind of an interesting section, and actually I kind of enjoy them, but students do find them somewhat challenging. So I want you to kind of take a minute and kind of get the wiggles out. Stand up if you need to, stretch, do whatever you need to do, because we're going to start something a little bit difficult. All right, so take a moment and kind of get ready for it. Okay, 3.8, implicit differentiation. What are we going to do in 3.8? In 3.8, the title gives it away. Implicit differentiation. Differentiation means we're going to take the derivative. Implicit is different from explicit. What we've been doing are explicit derivatives. We had a formula and we took the derivative of it directly. When it's implicit, it is implied, which means we're going to have to find the derivative in a roundabout or circuitous manner. And that's exactly what implicit differentiation does. So it is a skill that tends to show up more and more often the higher up in mathematics you go. However, it's not something that you will use on a daily basis. It's more a once every 3 to 4 weeks basis. It doesn't come up very often, but on occasion you need it. All right. So we've studied how to find equations of tangent lines. We've studied the rate of change of a function at a specific point, but we've always known exactly what the function was. We always had y equals some equation, and we had the point. We're still going to have the point, but we're no longer going to have y equals an equation. So the first thing we want to talk about is, what does it mean to have an explicit equation and an implicit equation? So I'm going to put the two definitions up here together. I don't know if I can get them on here at the same time, but I'll give it a shot. There we go. All right. This comes out of the Merriam-Webster dictionary. These are the definitions for explicit and implicit. And this does have a lot of effect on what we're talking about. Explicit means it's fully revealed. There's no vagueness. There's no implication. It's just right out front, stated directly. There's no ambiguity. It leaves no question as to meaning or intent. It is fully developed or formulated. In mathematics, explicit means you've defined an expression and it contains only the independent variable. So let me say that again. In mathematics, it means your expression has only the independent variable. For us, the independent variable is either x or t most of the time. So our expression has only x's in it or only t's in it. All right. What is implicit? This means it's capable of being understood from something else, even though it's not expressed directly. It's implied. It's involved in the nature of or essence of something, though it is not revealed, not expressed, not developed. It's potential. In a mathematical function, it's defined by an expression in which both the dependent variable, which is y, and one or more of the independent variables are not separated on opposite sides of the equation. So let me give you an example. Here is an explicit equation. I have the dependent variable y. Oh boy, I can't spell today. Dependent, I lost my inner syllable there, all on the left side only. And on the right side, I have only the independent variable. This is what we mean by explicit. I can explicitly separate these guys. Dependent variable, you stay over there on your side. Independent guys, you get over here on the other side and don't mix. All right, so we've got a complete separation of independent and dependent variables. When we talk about implicit, though, it's different. When we talk about implicit, we could have something that does something like this. There's no way in this second equation, x times the sine of y equal x squared y minus 5, to separate all the y's on the left and all the x's on the right. There's no way to pull these apart. If I try to get towards the y that's inside the trig function, then I'm going to bury the x squared y that is over here. There's no way for me to get these two y's together in one place. There's no way to solve this equation and write it explicitly as y equals something only involving x. This is an implied equation. It's probably still a function. Why? Because I took a function x and I multiplied it by a function, and then I added it and subtracted it with other functions. Combinations of functions are still functions, so it's probably still a function, but I cannot explicitly write it down in function notation. Remember, function notation replaces only the y, but the y has to be in one place and isolated. I can't get these in one place and isolated. So what is that going to mean for us? For us, it means that we're going to have to take the derivative in the form that it is and still find a way to get towards the dy dx, which is the derivative of y with respect to x. So we're still going to have to be able to get to our dy dx, even though it is not solved for y. All right. Let's take a look at some different equations. Sometimes it starts in an implied form, but it's easy to convert it to an explicit form. So for example, x minus y squared is not an explicit form because it doesn't have the form y on the left equals something with x only on the right. So it is an implied form, x minus y squared equals 0. But it's pretty easy to go ahead and isolate the y squared and get y squared equal x, and then solve for y by taking plus or minus the square root of x. Now it's solved for y, so this is an explicit form, whereas the original form was implicit. The second form is also implicit because it's not solved for y, it's solved for y squared. Now, if we look at this one below it, this is also one that can be solved explicitly, but this is not easy. This one is actually quite difficult to solve for y. If we look at this equation up here, this is the implicit form, x plus y cubed minus xy equal 1. We want to get the y's in one location where it says y equals stuff with x. But I don't have that yet. So the first thing we do is we isolate the y cubed minus 1. You may look at this and go, well, I would never think to do this. No, of course not. It took somebody weeks, if not months, to figure this out. This was not trivial. This was very hard. This took a long time to figure out. You're seeing the results of what they've done, but it would not probably occur to you to do this until you played around with it for a long time. So what they did was they isolated the y cubed minus 1, and they moved the xy to the right side with the minus x. Y cubed minus 1 is the difference of two cubes, which does factor, right? It has a formula, y minus 1, the cube root of y, the cube root of 1, and then you build the quadratic from the binomial. You square the first one, you multiply the two together, but take the opposite sign, and you square the last one. So this formula right here is a known formula for how to factor the difference of two cubes. On the right side, notice that we factor out the x, and that gives us a y minus 1. This gives us two of the same factor on opposite sides of the equation. And then we have to do something risky and something that introduces a restriction that was not there in the original problem. The original problem had no restrictions on x or y. But the next thing we're going to do is we're going to divide by the common factor y minus 1. Because we divide by it and we're not allowed to divide by 0, we've now added a restriction that y cannot equal a -1. All right. So we've added this restriction now that y cannot equal a -1. Now what do we have? We have y squared plus y plus 1 equal x. We equate what's left. Then we move the x to the left so we can get it in standard form because we're going to have to use the quadratic formula. I told you this is a nightmare. This is not simple on how to turn this into an explicit equation. Our a is the coefficient of the y squared term, which is 1. Our b is the coefficient of the y term, which is 1. Our c is everything else, which includes 1 minus x. So our c is actually an expression involving the variable x. Then we apply the quadratic formula, opposite of b plus or minus b squared minus 4 times a times c, all divided by 2a. When we simplify what's under the radical, we end up with this final expression down here, which I've split into 2 fractions. This now is an explicit formula because I have y equals on the left and something only involving x on the right. This is explicit. The original was implicit. But this was a tremendous amount of work. And it only worked in this equation because we added the restriction that y cannot equal 1. And it only worked because of the nature of this particular expression. This might not work in other cases. This technique might not work. So we need a way to find the derivative dy dx, even though we're starting from an implicit form. It also is necessary in cases where it's not just hard to write it explicitly, but it's impossible. I gave you an example of one earlier where it was impossible. And here's another example of a place where it is impossible to write this formula explicitly in terms of y. If I try to solve for the y that's in the power on the exponential, I could switch this into logarithmic form. And if I switch it into logarithmic form, then I would have the natural log, the base is e, the answer is 2y, and it equals the power, which is xy. But the problem is, this is now buried, the 2y, this y, inside of the natural log, and I can't get my hands on it. So there's no way for me to isolate both y's at the same time. I can isolate one y at a time, but not both. I can't get them together. It's impossible, all right? So I've written it in a different format, but it didn't help me any. I still have 2 y's on opposite sides. One's inside a natural log. The other is not buried inside of a function, but I can't get them together, all right? There's no way. So I've got a problem. This is technique that we're going to learn is called implicit differentiation. It's going to let us take the derivative without solving for y first. So remember, however, that the dependent variable y does depend on x. It is not a constant. This is not like that homework problem that you had where you had f of r is equal to, oh gosh, what was the formula? mv squared over r. Is that what it was? Okay, something like that. When you're looking at that, do you see how it has the r here in parentheses? That means that only the r is considered a variable and the m and the v are considered constants. This is not that case. In our case, both the y and the x are variables. They can both change. And because of that, we're going to have to invoke the chain rule. Basically, when we take the derivative with respect to x of y, we're going to get dy dx. We're not going to get 0. The derivative of that variable is not 0. It is dy dx. It is not constant. It is changing because it too depends on x. So when we take the derivative of y, we get dy dx. Here are the steps for solving using implicit differentiation. You're going to take the derivative of both sides of the equation. So take the derivative of the left, take the derivative of the right. Keep in mind that y is a function of x, so if you have a y, it becomes a dy dx. If you have a y squared, then you apply the chain rule. 2y dy dx, derivative of the outside function, 2 times something to the first power, freeze the inside at y, times derivative of the inside function, dy dx. So we're thinking of y as a function itself. So the derivative of y squared, again, chain rule, derivative of the outside, 2 times something raised to the first power, freeze the inside at y, then multiply by the derivative of the inside, dy dx. All right? So when we're looking at something like this, we have the derivative of sine of x equal to cosine of x. But the derivative of sine of y is a composed function. And that means that we have sine x on the outside and we have y on the inside. So the derivative becomes the cosine of y, freeze the inside, times the derivative of the inside function dy dx. We're using the chain rule. After you do the derivative of the left side and the right side, you're going to rewrite the equation so that all the terms that have a dy dx in them are on the left side, and any term that does not contain a dy dx, you'll move to the right. So you're going to isolate all terms that have dy dx on the left. Anything without dy dx goes to the right. You're trying to solve for dy dx. So the next thing you do is you factor out the dy dx on the left as a common factor. It's probably not going to be the greatest common factor. We don't want the greatest common factor. We want to isolate dy dx. So we pull out just dy dx, and then we divide both sides by its factor, whatever the algebraic expression is. So let's do this based on the formula x minus y squared. So we're going to look at x minus y squared, and we're going to think of the y squared as being the square of an outside function and the inside function being y by itself. All right. So we're not going to write it in explicit form. Remember, you can write it in explicit. This is implicit form. And our explicit form for this earlier was y equals plus or minus the square root of x. But we're going to start in implicit form. So we're going to apply the steps. Starting with the original, take the derivative of both sides of the equation. So we take the derivative of the left and the derivative of the right. Now the derivative of 0 is just 0, so that doesn't change. The derivative of x with respect to x is 1, but the derivative of y squared with respect to x is a composed function. The outside is the second power, so it's 2 times freeze the inside at y to the first times dy dx. This is applying the chain rule to anything involving y, right? Our next step is going to be to isolate the terms that have dy dx in them. One is a term separated by the subtraction. Negative 2y dy dx is a term separated by the subtraction and the equals, and 0 is a term. So we're going to isolate and separate the dy dx terms from the non-dy dx terms. This gives us 2y dy dx equals 1. The next thing we want to do is we want to factor out the dy dx, only the dy dx. We are not interested in taking out a greatest common factor. We're trying to isolate dy dx by itself. So we take that out and then we divide by whatever its coefficient is, in this case 2y. So this gives me dy dx equals 1 over 2y. This is still in some ways an implicit formula because it's not explicitly in terms of only x. Does everybody see that? This is not explicitly in terms of x. It's an implied formula in that I still have y involved in it, but this is the derivative of y with respect to x. Now, let's think about what we had explicitly. Explicitly, we had y equal to plus or minus the square root of x. And if we replace this in the formula, we have 1 over plus or minus 2 square root of x, which is an explicit formula. Right? Most of the time, when you apply implicit differentiation, your formula will have a mixture of both x's and y's in it. So the formula for the derivative is still implicit. It still has both x and y in it, which means if you want to find the equation of a tangent line, you'll need a point with both the x and the y coordinate because you'll need both of them to plug into the equation. You can't just know the x, right? So finding the slope of the tangent line. If you want to do that, you've got to know both parts of the point. You've got to know the 4 and the 2. In this case, it's the 2, the y value, that gets plugged into the formula, 1 over 2y, which gives the slope 1/4. Notice if I had solved this explicitly, I would still have a plus or minus, and I wouldn't know which part of the graph it's on, and I would have to figure that out from the context. I would have to look at the graph, decide if the slope's supposed to be positive or negative, and then I would have to figure out which one it is. So there are some advantages to doing the implicit formula, right? However, you did have to know both the x and y coordinate to use it. Let's take a look at example 1, which is 4x to the 5th plus tangent of y equals y squared plus 5x. This is an implicit formula because I have a mixture of x's and y's on both sides. But basically, it's always going to stay implicit because I've got y squared outside here, and I've also got y inside of a trig function. There's going to be no way to get these two y's together in one location and isolate it algebraically. There's no way to solve for y. So we're going to do the implied formula by taking the derivative of both sides of the equation. So when we do this, we take the derivative of both sides, which leads us to write the derivative with respect to x of 4x to the 5th plus the tangent of y equal the derivative with respect to x of y squared plus 5x. Right? Now we'll apply the derivative on each side, which is going to give me, applying it term by term, this is going to give me 20x to the 4th. Remember that anything that has y in it is actually a composed function. We have tangent on the outside, y on the inside. Derivative of tangent is secant squared. So I get secant squared of something, freeze the inside at y, and then multiply by the derivative of the inside function, which is dy dx. The derivative of our inside function being y will always be dy dx. On the right side, I again have a composed function. I have a square, and the inside function is y. Notice the y does not match the differential in the denominator of the derivative formula. That's a dead giveaway that you have to apply the chain rule. And that's going to give you 2 times something raised the power to 1. We're going to freeze the inside at y, and then we're going to multiply by dy dx. And then the derivative of 5x, x does match the differential in the denominator, so the derivative is just 5.
Sorry, I have a question. What do you mean when you say the differential? Okay.
Yeah, the differential is the dx in the denominator. That's what we're talking about when I say differential. We haven't discussed what the differential represents yet. We're not quite ready to do that. We will be doing that when we talk about the linear approximation function, which is coming up in section 4.2. So it's about 3 sections away. So we're getting really close to defining what the differential is, but we're not quite there yet. But the main thing to recognize is when the variable, and it has to be a variable, not a constant, when the variable doesn't match the differential, you have to invoke the chain rule. Right? Now we want to isolate our dy dx terms. So that means everything with dy dx is going to stay on the left side. So I have secant squared of y dy dx. And I'm going to move over the minus 2y dy dx by subtracting it. And I'm going to move everything else to the right side. That's the 5 minus 20x to the fourth. The two terms on the left now have dy dx in them. The two terms on the right do not. Now I want to isolate dy dx by factoring it out. So I factor out the dy dx, and that leaves behind secant squared of y minus 2y equal 5 minus 20x to the fourth. Nothing happens on the right side. It only happens on the left side. And then the last step is to divide by the coefficient of dy dx to isolate dy dx. So I get dy dx is equal to 5 minus 20x to the fourth divided by secant squared of y minus 2y. And you'll notice this is still an implicit formula because it has a mixture of both x's and y's in it. All right, so it's not an explicit formula, it's implicit. All right. Let's take a look at one more example. Dy dx, we want to find dy dx for the implicit equation xy minus cosine of xy equal 1. So we're going to take the derivative of both sides. And that gives us the derivative with respect to x of xy minus cosine of xy equal to the derivative with respect to x of 1. On the first one, I have to apply the product rule. So remember, this is going to be like my f and this is like my g. So I'm going to have f prime g, which is 1 times y, plus g prime f, and g prime is dy dx, minus, and now I have to have the derivative of cosine. The derivative of negative cosine is going to be a positive sign. I freeze the inside at xy, and then I multiply this by the derivative of xy, which is again 1 times y plus dy dx times x. This is going to equal 0 because the derivative of the constant 1 is just 0. So I've had to apply the product rule twice on the product of x times y because they're both variables and they both change value. Okay. Now I need to isolate these dy dx's somehow. So the first thing I need to do before I do anything else is I've got to simplify this and get some of those out of parentheses. So I have y by itself plus x dy dx plus y sine of xy plus x dy dx sine of xy equals 0. The next thing that I want to do is I want to isolate the dy dx terms. Anything with dy dx in it is going to stay on the left, and anything without it is going to move to the right. The next thing we want to do is isolate the dy dx by factoring it out. So I isolate dy dx by factoring it out. That leaves me x plus x sine of xy in parentheses equal to the right side negative y minus y sine of xy. And the last step is to divide by the coefficient. So we're truly isolating dy dx. So I have negative y minus y sine of xy divided by x plus x sine of xy. Nothing will reduce. Don't even be tempted to cancel those sine of xy's because they're both inside of terms being added or subtracted to something else. So it's hands off. Either the whole thing goes or none of it goes. All right. So it is a more complicated process, and it does lead to an implied formula with both x and y. So next we're going to look at example 3. Let's take a look at example 3. We're here in the implicit differentiation section. So we'll remember the steps to doing our implicit differentiation. We take the derivative of both sides, then we simplify the sides, then we isolate all the terms that have dy dx in them by moving them to one side and moving terms without dy dx to the other side. Then we factor off the dy dx to isolate it. Then we divide both sides by the coefficient of dy dx. So we want to look at this equation, y sine of xy equal y squared plus 2. Now this is an implicit equation because you've got both y and x in various places throughout the problem, and it's not solved explicitly for y. It's not y equals. There's no way, in fact, to solve this one for y alone because you've got y inside of the trig function and you've got y outside the trig function in two places. So there would be no way to solve this one for y. It's simply impossible. I have no idea what this looks like. We might graph it just for fun to see what it looks like. But in the meantime, let's see what we can do to find the derivative of it. So the first thing that we're going to do is take the derivative of both sides. All right. So we take the derivative with respect to x of the left side of the equation, which is a product between y and the sine of xy. And then we take the derivative of the right side, which is a sum y squared plus 2. So this is going to give us, you can think of this as f, and you can think of the sine of xy as g. And inside of that, there's another product rule. So we're going to have a product between y and sine, and then we have the chain rule with sine on the outside and xy on the inside. And then we're going to have, when we do the derivative of the inside, we're going to have another product rule, which is xy. So this one is going to take up quite a bit of space. So we're going to have f prime and g. So f prime derivative of y is 1 dy dx times sine of xy. So this is my f prime, and this is my g, plus, and now I need to do g prime. So g, oops, I should have written that below and not in that space. So g prime, and g prime is going to be the derivative of sine of xy. So invoking chain rule, derivative of the outside, derivative of sine is cosine, freeze the inside, times the derivative of the inside, which is another product rule. So then we have this one as an f and a g, and then we're going to have the derivative of x, which is 1 times y, plus the derivative of y, which is dy dx, times the x. All right. Now that finishes g prime for the outside product. All right. So again, We took the derivative of sine, which is cosine. We froze the inside at xy. Then we took the derivative of the inside, which is 1y plus dy dx times x. Now we multiply that by y. So that's our f for the outside. Right? And then on the other side, we have the derivative of y squared. The derivative of y squared, you treat this like a chain rule, like a composed function. So the 2 comes to the front and becomes 2y to the first. And the derivative of the inside function is y. So it's dy dx. So we get 2y dy dx. The derivative of 2, of course, being a constant, just gives us 0. So the next thing we want to do is simplify a little bit. We want to get rid of the parentheses so that all our terms that have dy dx in them are out in the open and not buried inside parentheses. And we're going to rewrite things a little bit so that the order makes more sense. So we have the sine of xy times dy dx for the first term, plus now we're going to distribute this cosine over the parentheses that are here. And remember that the y is a part of this as well. So we're going to have y cosine of xy distributed over the other y, which gives us y squared. So we have y squared cosine of xy. And then we're going to multiply the y cosine of xy by the second part, which would give us plus y cosine of xy multiplied by dy dx times x. So that gives us an x, which we can put at the front, and a dy dx, which we can put at the back. And then this is equal to 2y dy dx. Remember in multiplication that the order is not important, that it can commute and associate, so we can move around the factors from the back to the front. Okay. Our next step after we simplify is to isolate the dy dx terms. That means any term that has dy dx in it needs to go to the left side, and any term that has no dy dx needs to go to the right side. So the first term has dy dx, so we leave it on the left. So we have sine of xy dy dx. The next term does not have dy dx, so we're going to move it to the other side. So we're going to have a negative y squared cosine of xy on the right side. The third term does have dy dx, so it stays put. So we get plus xy cosine of xy times dy dx. And the fourth term, which was on the right-hand side, also has dy dx, so it needs to move to the left by subtracting it. So finally, we have minus 2y dy dx. Our next step is to isolate the dy dx. So we want to pull the dy dx out and get it by itself. We are not looking for the greatest common factor. We're looking only for dy dx. We're trying to isolate dy dx. So we factor that off of the left side. Again, we are not looking for a common factor. So even if we had one, we would not take it out. In this case, I don't believe we do have a common factor. All right. Now this is a pretty complicated derivative. When you do implicit differentiation, the formulas can be quite complicated and not at all simple. So the last step that we have to follow is to isolate dy dx by dividing by the coefficient of dy dx. So we want to divide by the coefficient of dy dx. And that will completely isolate our dy dx. So now we have that the derivative of y with respect to x is equal to negative y squared cosine of xy, the right side, divided by the factor that was on the left side on dy dx. Sine of xy plus xy cosine of xy minus 2y. So this is a formula that represents the derivative of the original y with respect to x. So even though we weren't able to solve this equation for y, we were still able to get a formula that will give us the derivative of y with respect to x. And this, of course, represents the slope of the tangent line to the curve at any particular point. But this has both x and y in it. So if I want to find the slope of the tangent line at a point, then I will have to know both the x coordinate and the y coordinate. And then I'll plug those values in and get a value, and that will give me the slope at a particular point. All right.
Can you go back to when you distributed cosine xy through 1 times y?
Yes, this step right here.
Yeah, how did that end up with y squared cosine xy?
Okay, so let me write it in a different color underneath. Okay, so let's see if I can add a line in here. It will let me. Yeah, looks like I can. All right, and this was my F. All right, so another way of thinking about this step right here is simply to take the y that's at the back, since it's multiplied, you have a cosine of xy, you have everything in the brackets, and then you have another y. You could move the y that's at the back to the front, y cosine of xy times y plus x dy dx. And let's see if I've made a mistake or not. So when I distribute the y cosine of xy over the parentheses, I get a y squared cosine of xy. Okay. So, and then when I distribute over the next term, I get an xy cosine of xy dy dx. Right? Does that help? Writing it, yeah, just adding in that extra step sometimes will clarify and make it more clear. All right. Okay, just for fun, let's see what this does look like. We've got sine, y sine of xy. Let's see if Desmos can handle this. Y sine of xy equal y squared plus 2. Isn't that what it was? Y sine of xy equal y squared plus 2. I'm not seeing anything. Are you guys seeing anything?
Nope.
Oh, wait. This equation has fine detail that has not been fully resolved. It's here somewhere. Interesting. I was hoping it would pop up if I just left it there for a little while. Sometimes they have so much detail that Desmos can't handle it. So let's leave it for a second and see if Desmos can come up with something. But if not, it may just be too complicated for Desmos to graph. There are other graphing calculators that might be able to handle it. I'm trying to think, GeoGebra might handle it a little bit better than Desmos. I'm a little surprised Desmos can't handle it though. Okay. let's take a look at the next one and we'll come back to the graph and see if it ever produced anything. Okay, our next example is number 4. We're doing exactly the same thing. We're just working through a lot of examples since this is more complicated. So the first thing we want to do, of course, is take the derivative of both sides. And that's the derivative with respect to x, not the derivative of y with respect to x. All right. So we're going to take the derivative of both sides of the equation. So we have the derivative with respect to x of the left, which is x cubed y plus xy cubed equal to -8. And we're going to take the derivative as well of the -8. Now, on this particular problem, it might, I was going to say it might be possible to try to solve it in some sort of fashion, but I don't think so. Looking at it again, I can't think of a way. I mean, we could factor out 1y, but that would still leave a y squared behind. I can't think of a way to get y isolated by itself in only one place. So I would still have it in 2 places. So I don't think there's a way that I can see of. There's no tricky technique that would let us solve this one for y alone. So implicit differentiation is the way to go. So we take the derivative of the equation as it currently stands, and then we simplify. So when we take the derivative, we end up with product rule for the first one. So this is going to give me 3x squared, that's my f prime, times y, that's my g, plus, then I'm going to have the derivative of y, which is dy dx, and that's g prime, times x cubed, which is my f. So this is the product rule on the first term. So 3x squared times y plus dy dx times x cubed. And then I've got a product rule on the second term on the left side. So I repeat this. So the derivative of x is 1 times y cubed. That's f prime g plus g prime f. And g prime in this case is going to be 3y squared dy dx times f, which is x. All right. And then our right-hand side of the equation is going to be 0. Since it's a constant, the derivative of a constant is 0. So remember, when applying the chain or the product rule here, that the derivative of the y cubed part is treated like a chain rule problem with something cubed on the outside. So you get 3 times the something squared. And then the derivative of the inside, which is y, gives you dy dx. Okay. Now we go ahead and re-simplify this, kind of reorder it a little bit. So we have 3x squared y plus x cubed dy dx plus y cubed plus 3xy squared dy dx equals 0. Our next step is to isolate the dy dx terms. We're trying to get dy dx by itself. So first we isolate the terms that have dy dx in them by leaving them on the left or moving them to the left and moving everything else to the right. So this is going to give me an x cubed dy dx on the left and leave the 3xy squared dy dx on the left. And it's going to move the 3x squared y to the right and make it negative. And move the y cubed to the right and make it negative as well. All right, so we've isolated the 2 terms that have dy dx in them. And the next thing we want to do is factor out the dy dx and isolate it. We are not looking for a greatest common factor. When we look at this particular problem, notice that x is a common factor on the left. Both of these terms have x. We do not want to take the x out. We only want dy dx. All right. So then we factor out dy dx to isolate it. This is basic warfare technique, right? Divide and conquer, isolate to annihilate. That's sort of the way we think of it. So we have dy dx on the left times x cubed plus 3xy squared equal to the right side, negative 3x squared y minus y cubed. Our final step then is to go ahead and divide both sides by the coefficient of dy dx. And this will give us our final formula for the derivative. So we have dy dx isolated on the left side by itself equal to negative 3x squared y minus y cubed, all divided by the quantity x cubed plus 3xy squared. Close the quantity. Now, the next thing you might want to look at is determine whether or not there's something that could cancel on the right side. X is not a common factor in the numerator because it's only in the first term, but not the second one. So even though the denominator has a common x, I don't have a common x in the numerator, so x can't cancel. In the numerator, I do have a common y, since y is common in both terms, but in the denominator, it is not common in both terms. So I cannot cancel a y either. So nothing cancels as far as what we have here in the expression on the right side. This is simply the equation as it is. And just out of curiosity, let's see if Desmos ever got anything. It never did it? It just can't handle that equation. Let's see if it can handle this one for fun. X cubed y plus xy cubed equal negative 8. Okay, x cubed y plus, what was it? xy cubed?
Yeah, equals negative 8.
Ah, okay, so it did. It almost looks like a rational function, but notice the curvature of the function in here in this section. It gets flatter here. It's got some kind of weird thing going on with the curvature. So it's not exactly a rational function shape. So when you're looking at it, it does look like it's approaching x as an asymptote here. And that makes sense because in our formula over here, if we were looking at the derivative and we had x equals 0, then the slope of the tangent line would be infinite, right? Because the derivative has a common x in the denominator. So if x were 0, that would give us infinity for the slope of the tangent line. And also we can see that it's approaching the x-axis or approaching y equals 0 as an asymptote as well. So we could actually compute the derivative at a particular point if we could find an exact point to do that at, which it doesn't seem to want to give me any particular points. It's having a little bit of trouble trying to compute points. So even though it does have points, it doesn't want to give any of them to me. I was hoping it would tell me what it was when x is 1, but it is not doing that so that we could find the slope and show the tangent line. But it is just not cooperating along those lines. So we're going to leave it as is.
I have a question.
Yeah, go ahead.
So we put dy dx every time we take the derivative of y, right?
That's correct. You have a dy dx every time you take the derivative of y, because you're taking the derivative with respect to x, and y is not x. So the dy dx is always left behind.
Okay, so we do the derivative and then we put dy dx.
And then you put a dy dx.
Okay.
Whenever you have a y, you have a dy dx.
Yeah, okay, correct.
Okay. Let's take a look at example 5. Example 5 is one that has we're asked to find the tangent line at a particular point. So this one, hopefully, Desmos will be a little kinder to us at evaluating. And we're given a point that is on the graph. So for example, when x is 2, y is supposed to be a -3. So you can plug that into the equation and see whether or not it gives you a true statement. It should. If x is 2, then we have, well, let's just check it real fast. This would give us 2 times -3 squared plus the sine of -3 pi, since we have pi y, minus 2x squared, which would be -2 times 2 squared. And this is supposed to equal equal 10, positive 10. So this would give me 2 times 9, which would give me 18. And the sine of a -3 pi, remember that -3 pi, you're going clockwise. So there's 1 pi, there's 2 pi, there's 3 pi. You end up out there at the same coterminal with pi. And the sign of that is 0 because it's the y value. So we get a 0 for this. And then we have -2 times 2 squared, which is 4. So that gives us -8. So we have 18 plus 0 minus 8. That does equal 10. All right. So that point is on that curve somewhere. And what we want to do now is we want to find the equation of the tangent line. Okay. So we're going to follow the steps that we followed before. The first thing we're going to do is we're going to take the derivative of both sides of the equation with respect to x. So we take the derivative with respect to x of the left side, xy squared plus sine of pi y. Remember, pi is a constant, not a variable, minus 2x squared equal the derivative with respect to x of 10. Now 10 is a constant, so that one's going to give us 0. On the left side, the first thing we have is a product, x times y squared. Y squared is going to be treated like the chain rule. The derivative of the squared is going to give us 2 times y to the first. And then because we have a y, like Juan said, we just tack on a dy dx, derivative of the inside function. So when we take the derivative, this is product rule. So we get f prime, which is 1 times y squared. That's our f prime g. Plus, now we need g prime, which is going to be 2y dy dx. That's our g prime times f, which is x. Then we have the sine of pi y, but pi is a constant. Think of it like a 4. It's like a 4y. So we take the derivative of the outside. This is chain rule. Derivative of the outside is cosine. Freeze the inside, stays frozen. This is a good metaphor for today since we have lots of snow outside. It is still snowing at my house. And then we multiply this by the derivative of the inside, which is pi y. The derivative of pi y would be pi times another dy dx. Since we have a y there, we're always going to have a dy dx attached. All right. Then the next thing that we have is a -2x squared. So the derivative of that, since it is x, is simply -4x. And then this is equal to 0. Then we can simplify and clean it up a little bit. We have y squared. We want to reorder the factors in the multiplication of the second term. So we have 2xy dy dx. We want to reorder the multiplication in the third term and move the pi to the front, then multiply by the cosine of pi y, and then leave the dy dx at the back. minus 4x equals 0. Right? Our next step is to isolate all the dy dx terms. So the y squared is going to move over here to the right-hand side, and the 4x will as well. So we end up with 4x minus y squared on the right, 2xy dy dx, plus pi cosine of pi y dy dx on the left. And the next thing we want to do is factor out the dy dx, only dy dx. We're not looking for a common factor. We're only wanting to isolate dy dx. So this gives us dy dx times the quantity 2xy plus pi cosine of pi y equal to 4x minus y squared. Our next step is going to be to divide by the coefficient of the dy dx. So this isolates the dy dx by itself on the left side, and it's equal to 4x minus y squared, all divided by 2xy minus pi cosine of pi y. There is nothing that will cancel. You do not have any common factors in the numerator, and you have no common factors in the denominator. This y is buried inside the trig function, so it cannot be factored out under any circumstances. All right. Now our job is to find the tangent line. To get the tangent line, we need a point, which we have. I believe it was 2, -3. So we have our point, but we also need the slope of the tangent line. So we have the point. What we need now is the slope of the tangent line. And this is going to be the derivative with respect to x evaluated at the point 2, -3. That's what this long vertical bar represents, to evaluate the derivative at the point 2, -3. So we're going to plug in the point. So dy dx at 2, -3. And I'm probably going to need another couple lines for the equation, is going to give me 4 times 2 minus a -3 squared. Do not do this in your head. Make sure you write it out, because if you do it in your head, you are highly likely to make at least one sign error. And then we have -3 times pi inside these parentheses. All right. So 4 times, go ahead.
So I'm just gonna ask, is it plus pi cosine or is it minus?
Oh, good catch. Thank you. It is plus. I made a typo there. All right. Okay. So we have 8 minus 9 in the numerator, which will give us a -1, over 4 times -3, which will give us a -12. The cosine of -3 pi is a -1. So this becomes minus pi, right? The cosine of -3 pi is a -1. So I get a -1 over -12 minus pi. And if I want to, I can take the -1 and move it to the denominator, and I can multiply both terms in the denominator by the -1, and that would give me 12 plus pi in the denominator. Unless I messed up a sign somewhere. Did I mess up a sign somewhere? Oh, this should be a plus. That's what's wrong. And so this one is a minus. All right.
But shouldn't
Did
it
I mess
be
up
a
another
negative?
sign?
I think it was a negative because it was -1.
Oh, you're
on
right. You're right.
cosine.
Okay, so let
So
me go
that's why
back
you have
and
negative.
let's go back and check and just be sure, because I've changed signs so many times I'm not sure anymore. So 8 minus a positive 9, that's correct. -12, that's correct. And it is -3, right? Our point? Yes. Okay. And then pi cosine of -3 pi, which gives me a -1. So that should be negative pi. So this was a -1. And that would make that plus. So I have 1/12 plus pi. Do I get agreement?
Yeah, it's just you forget when you simplify the -1 in the denominator, you forget to put the negative in the top, so it feels like
Yeah. So
you're
it feels
forgetting
like
it.
I've made a
So
mistake, but it looks okay now.
yeah,
All right, so let's graph this problem and see what it looks like. So we have xy squared plus sine of pi y. So I'm going to take these off. And I've already forgotten what it is. Let's scooch this over so I can see it. Xy squared plus sine of pi y Ooh, that's a weird looking graph. Look at that. Isn't that cool? Look at that. Okay, sorry. I'm such a nerd, but it's really cool. All right, minus 2x squared. Oh, now that is really sick. I'm sorry, but that's seriously cool. I mean, okay. I'm just having fun here myself. All right, equals 10. Did it handle it or not? Oh, I've got an equals at the beginning. And this should be a plus. I have to say though, that was a really neat graph. Okay, so I've got xy squared plus sine of pi y minus 2x squared equal 10. All right, this one's not nearly as cool as the one I had before. All right, so here is our graph. It's got some kind of weird change in curvature that's going on right in this section right here and right in this section right here. But at any rate, we can see the graph. Let's try blowing up the graph a little bit as far as the y-axis goes. So let's make the y-axis maybe go up to 27 or something like that, but zoom in a little bit. Okay, so we can see more of it at the same time. Okay, and now we want the point 2, -3, I believe, which is right there on the graph. So we'll label that point. And now we need to come up with our equation. So remember, for the equation, you're going to do y minus y1. So y minus a -3 would be +3, equal to the slope of our tangent line, which is going to be 1 divided by, and was it 12 plus pi? Yeah, okay. 1 divided by 12 plus pi multiplied by x minus 2. And there it is. And you can see that it is in fact tangent right here. It's barely skimming the surface of this curve at that one point, which is kind of wild. Anyway, it was kind of fun playing with that because that gave us some seriously cool things in the interim. I really liked the one that had the circle in the middle and then the 2 separate pieces. That was pretty awesome. All right, so it's kind of fun to play around with this stuff. All right, so we've got a graph of this, and we can add this to our notes so that we can remember what it looks like. So we can add that down here. And we can also add into the notes the equation of the tangent line. Y minus a -3 equals slope of the tangent line, 1/12 plus pi, x minus 2, which you can write the double negative as a plus as well. Okay. Let's take a look at example 6 really quickly, and then we'll move on to the next one. In example 6, we're finding the equation of the line tangent to the hyperbola x² minus y² equals 16 at the point 5, 3. Then we use technology to graph both the hyperbola and the tangent line. So same basic thing. Now we could solve this one explicitly for y, but if we do, we're going to end up with a plus or minus a square root, which makes it kind of, well, just not very much fun. And then we'll have to decide whether it's the plus or the minus, because it can't be both. It can only be one. So doing it implicitly may give us a different kind of formula where we need both x and y, but it will take away the ambiguity of the plus or minus. So we're going to do this one with implicit differentiation, and we're going to take the derivative of both sides. So this is going to give me the derivative of x² minus y² equal to the derivative with respect to x of 16, which gives me 2x minus 2y dy dx equal to 0. Then we're going to isolate our dy dx terms. And that's going to give me 2y dy dx equal to 2x. I like to have my dy dx's on the left. It doesn't really matter as long as they're separated. And then we're going to factor off the dy dx. So that gives me dy dx times 2y equals 2x. And then the next thing that I want to do is I want to divide by the coefficient of dy dx.
Shouldn't it be -2y right there again?
I moved the 2y dy dx to the other side, which made it positive from this step.
The
So
second step? Or to the from the second to the third?
From the second to the third. So when I add the 2y dy dx to the other side, it becomes positive. All right. And then I swap sides. So I moved it to the right, and then I just swapped the sides, which one was on which side. So it should still be positive. Okay. And when we divide by the coefficient, we end up with 2x divided by 2y, which does reduce to x over y. Now we're asked to find the slope of the tangent line, the equation of the tangent line at the point 5, 3. So we have a point 5, 3, and we need the slope of the tangent line evaluated at 5, 3. And that will give me slope of the tangent line, which is the derivative dy dx evaluated at 5, 3, is going to give me 5 divided by 3, which is 5/3. So my equation is going to be y minus 3 equal 5/3 x minus 5. That's the equation of my tangent line. So let's take a look at it. X² minus y² equals 16. And hopefully you remember from when we were in trigonometry, we did the conic sections. So hopefully you remember that x squared minus y squared equals 16 is the equation of a hyperbola. Because one's positive and one's negative. And then we had the point 5, 3, which is right there. Looks like it's on the right arm of the hyperbola. And then the equation of our tangent line was y minus 3 equal to 5/3 x minus 5. And there it is, tangent to our point at 5/3. All right, and you can see that it is in fact tangent to that point.
What happens when you plug dy dx back into your simplified version?
What happens when I take dy dx?
Yeah, so you have dy dx as x over y. What happens if you plug that back into your like simplified derivative when you still have dy dx in it?
I'm not sure. When I plug it into a simplified what? Into which part?
The first step when you have dy dx in there.
Oh, I see. If I were to replace this up here with dy dx, I would
Yeah.
get a true statement, something that's true. All right. So for example, let's just do it over here to the side. I'll change color so it pops out. So Trevor is asking what would happen if I were to replace dy dx here at this step with what it's equal to, which is x over y. And what would happen is you would get a true statement. So you would work this out, the y's would cancel, and you get 2x minus 2x equals 0, which is true. That's what would happen. You wouldn't get a solution of any kind, but you would get something that's true, which lets you know that that is in fact the derivative formula, right? That it does work. It is the solution. Okay. All right. Let's take a look at another one. This one is a little bit simpler than some of the ones we've done before. Some of the ones we did before, remember, Desmos just couldn't handle it. It couldn't graph it. It was too complicated. This one probably it can handle. Tangent of xy equals x plus y, but it is always going to be implicit because the y is buried inside the trig function and outside the trig function. When it's both inside a function and outside, there's no way to isolate it in one place only. If it were only inside, I could do arctangent. If it were only outside, I could solve for it. But when it's both inside another function and outside the function, then I can't do anything. It's going to have to stay implicit. So we want to find the equation of the tangent line on this one. So we start same steps, take the derivative of both sides. And this is going to give us the derivative of tangent of xy. The inside of the chain rule is going to invoke product rule. And then we have the derivative of a sum. Okay. So if I take this, I would get the derivative of tangent is secant squared. So I get secant squared, freeze the inside, times derivative of the inside is product rule. So I get derivative of x, which is 1 times y, plus the derivative of y, which is dy dx, times the first, which is x, equal to the derivative of x is 1, and the derivative of y is dy dx. Then we simplify. And this would give me y secant squared of xy plus x secant squared of xy times a dy dx equal to 1 plus dy dx. isolate your dy dx terms. Which would give me x secant squared of xy dy dx minus dy dx equal to 1 minus y secant squared of xy. The next thing is to isolate dy dx by factoring it out. We're only after dy dx, that's what we're trying to isolate. So even if there is a greatest common factor, we don't take it out. Notice this leaves a -1 behind in parentheses, since you have to have a placeholder for each term. Then we divide by the coefficient of dy dx. So we have dy dx equals 1 minus y secant squared of xy divided by x secant squared of xy minus 1. Because of the ones, we're not going to have any common factors in the numerator or denominator that we can cancel. We are supposed to look at this point at the point 0, 0. 0, 0 does work in the original. The tangent of x times y, 0 times 0 is 0. The tangent of 0 is 0, and 0 plus 0 is also 0. So 0, 0 is on the graph of this equation. So let's put it over here. So I have tangent of xy equal x plus y. Now I knew this one would take a little while. So this is what I meant by sometimes the graphs are so complicated that it just can't handle all the detail. This is an example of one where it's really having a hard time with the level of detail. Where you see these dots, there really are not dots. These are actually supposed to be connected. This actually looks like a contour plot. And we're looking at the point 0, 0. So we're looking here at the origin. All right. And this is an enormously complicated curve. It's not actually a function after all. It certainly doesn't pass the vertical line test, but it is a curve. If you want to call it something, we call it a curve. All right, even though it's got multiple curves on it. Let's take a look now at finding the equation of the tangent line at the origin. So we have our point, which is 0, 0. It was given to us. And now we need the slope of the tangent line at that point. So we take the derivative formula and we replace x with 0 and y with 0. So this gives me 1 minus 0 times the secant squared of 0 times 0 over 0 times the secant squared of 0 times 0 minus 1. 0 times anything is going to be 0. So I get 1 over -1, which is a -1. So the equation of my tangent line is y minus 0 equal -1 x minus 0, which simply becomes y equal -x. Right? So take a moment and write that down. We found the slope of the tangent line by replacing x and y with 0 and 0. We multiplied out the arithmetic and the algebra, and that gave us a slope of -1. This is at the origin, so the coordinates disappear, and we get simply y equals -x. So let's look at this really wild graph, and let's add to this our tangent line and see if it is actually tangent at that point. And of course it is. All right. So we have y equal -x, and it's definitely tangent at that point. right? And this is certainly one that you might want to take a picture of because you certainly wouldn't want to hand draw that. There's way too much detail. And again, Desmos is having a really hard time with this one because of all the fine detail in it. These, where you see these dots and these disconnections, it actually should be connected. It's just having a hard time drawing it, right? You would need something like Mathematica, which is far more high powered than Desmos. It makes Desmos look like a little tiny 4-function calculator compared to a graphing calculator. And that may not even be strong enough. Mathematica is a super powerful piece of software for mathematical functioning. Okay. Let's look at example 8. We're looking at the volume of a right circular cone of radius x and height y. So when we're thinking about this, we can think about this as a cone like this, and it has radius of x, and it has height coming down from the top, and the height is y, all right? Now the volume of a cone is 1/3 pi r squared times the height. So in our case, because the radius is x, we can write the volume as 1/3 pi x squared, and the height is y. So we can write it as 1/3 pi x squared y. But it's basically what's called a pyramid shape, where the cross sections are all circles, but they get smaller and smaller until it comes to a point. And so when you do the cross section of something like that, it's 1/3 area of the base, which is pi r squared, the circle, times the height. That's the formula. Whatever the pyramid is, 1/3 area of the base times the height. Now we want to suppose that the volume of the cone is a constant. All right. This is a constant value, not a variable. So x is changing and y is changing, but v is not. V is held constant. We don't know what v is, but let's pretend v is 20 cubic inches. Then v is always 20. So when we take the derivative of it, it's going to go to 0. We want to find dy dx when x is 4 and y is 16. So first we take the derivative of both sides of the equation with respect to x. So we're going to take the derivative of the volume, v, and then we're going to take the derivative of 1/3 pi x squared y. V is a constant, so the derivative of it gives us 0. On the right side, pi is a constant, so we have the product rule really between x squared and y, and the 1/3 pi is a factor on each. I'm going to pull the 1/3 pi along with the x squared as part of f, and I'll let y by itself be g, the second factor. So this is going to give me the derivative of f, bring the 2 to the front. So I get 2/3 pi x times y. So this is my f prime g plus, now I need g prime. The derivative of y is dy dx, and then times f, which is 1/3 pi x squared. All right. My next step is to isolate my dy dx terms because I don't really need to simplify it much. I could simplify it a little bit. Let's simplify. I would probably move the 0 over to the other side. So I would have 2/3 pi xy plus 1/3 pi x squared dy dx. That's probably how I would write it, equals 0. And then we want to isolate the dy dx term. When I move the other to the right side, it becomes negative. So I have negative 2/3 pi xy on the right and 1/3 pi x squared dy dx on the left. The next thing I want to do is I want to isolate dy dx by factoring it out. So this gives me dy dx times 1/3 pi x squared equal negative 2/3 pi xy. The next thing I want to do is divide by the coefficient of dy dx. Which is going to give me dy dx equal to negative 2/3 pi xy divided by 1/3 pi x squared. Right? Now we need to do a little bit of algebra to sort of clean this one up a little bit because we've got some common factors here. One thing I could do is I could multiply both the top and the bottom by 3/1 over 3/1. And that is equal to 1, but it will get rid of the 1/3 factor. So when I multiply by it, I'm going to get negative 2 pi xy in the numerator and 1 pi x squared in the denominator. The 3's will cancel and go away. Then I've got a common factor of pi, so the pi's cancel, and I have one common factor of x. So the x cancels from the numerator, and one of the x's cancels from the denominator. So my final formula for the derivative dy dx is negative 2y divided by x, which is actually a quite simple formula, surprisingly. It's much simpler than what I was expecting. Now, the last part is it wants to know what dy dx is when x equals 4 and y equals 16. So we want to find dy dx when x equals 4 and y equals 16. So we replace y with 16 and we replace x with 4, and this gives me a negative 8. Now, let's interpret what this dy dx is saying. Dy dx is a rate of change. Y represents the height and x represents the radius. So the height is decreasing by 8 units. For every 1 unit, the radius increases. That's basically what dy dx represents. It's the rate of change of the height of this cone with respect to the radius. As you make the radius larger, you have to decrease the height to keep the volume of the cone a constant. So if you want the volume of the cone to be a constant, you have to kind of compensate for making one of them larger by making the other one smaller. And in fact, you've got to make the height much smaller for a small increase in the radius. An increase of 1 in the radius requires a decrease in the height by 8 units. Okay.
Sorry, I have a question. When
Go
you
ahead,
take
Juan.
when you take the derivative of 1/3 pi x squared, I didn't get why you only get 2/3 pi x. Yeah.
When I took the derivative of up here, when I took the derivative of 1/3 pi x squared,
Yeah, I know the first, I don't know if you do like because the first two go to 0 and then just the third one will be it's just because there are 3 factors. I don't get how you
I'm not
do that.
thinking of it as 3 factors. I'm thinking
Okay.
of it as 2 factors. 1/3 pi x squared and y. So 1/3 pi is a constant. Constants just tag along. They don't affect the value of the derivative. They multiply by the derivative, but they don't affect the value of it. This is that scalar multiple property. So pi is not a variable. So for example, if this had been, let me do another example down here to make it a little bit clearer. Where can I write? Right there, I'll write up above. If this had instead been 4x squared, what would you do for the derivative?
Oh yeah, 8x.
8x.
I see
So
it.
again, you're just multiplying the power by the constant. Pi over 3 is just a constant, just like 4. So I just multiply it by the 2, and that gives me the 2/3 pi, then times x.
Okay, yeah, perfect. Thanks.
Okay,
Oh,
yeah,
I'll know
having
that.
pi as a symbol really messes students up. A lot of students make the mistake of thinking that because it's a symbol, it's got to be a variable, but it is not. It's a constant. Okay. Let's get to another one that also messes students up, and that's the exponential, which is also a constant, but represented with the symbol E. So E is called Euler's number for Leonhard Euler, who is one of the most prolific mathematicians of all time. He was phenomenal, 2.7, hang on, 2.71828 1828459, blah, 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 blah. It is an irrational number. Euler was a truly amazing mathematician. He's very rare. Most mathematicians in the course of history do their best work in their 20s. I know that sounds crazy, but this includes Newton and Einstein. They did their most phenomenal work, their most groundbreaking work in their 20s, in some sense, before they knew enough to really know what they were doing. So it sort of allowed them to think outside the box and consider things that hadn't been considered before. It's rare to find a mathematician in history who was doing as much important work in their 40s, 50s, and 60s as they were in their 20s. But Euler is an exception. He worked until his 80s and was just as prolific at the end of his life as he was at the beginning. And what makes it even more incredible is that he was blind for the last 20 years of his life. So he could not write down what he was doing. He dictated what he was thinking to an assistant who wrote it down. And he was just as prolific in those last 20 years as in the previous part of his life. He is a big, big name in mathematics. So if you ever want to read about someone who had a fascinating life, Leonhard Euler is definitely one. So we've named this the exponential number, and we use the symbol E. This is Euler's number, and it is pronounced Euler. Please don't say Euler. That's not correct, okay? It's a German name. So it's Euler, like O-I-L-E-R, but spelled E-U-L-E-R. So this is E, but it is a constant like pi. It's irrational, but it's a constant. So when we have this function, e to the xy equal 2y, we have a problem because we again have the y inside of a function, composed inside the function in the power on the exponential, and we have it outside the exponential. So there's no way to solve this for y in one place only. If we tried to switch to natural log form, it would reveal the y that's in the power here, but it would bury the 2y over here and put it inside of the natural log. So there's no way to solve for y. So to find the derivative, we do implicit differentiation. and we take the derivative of both sides. So it's a deceptively simple formula or equation, but it's actually quite complicated. So we have the derivative of e to the xy equal to the derivative with respect to x of 2y. Now we haven't handled an exponential with the power before, but this is one of the things we'll be talking about today. When you do the derivative of e to the u, the derivative with respect to x of e to the u is e to the u times the derivative of the inside function. In other words, the derivative of the power. So it stays the same. The derivative of an exponential is the exponential times the derivative of the power. So when we take the derivative of e to the xy and we simplify, we get e to the xy times the derivative of xy. And the derivative of xy is the product rule. So we get 1 times y plus dy dx times x. All right. So this is our e to the u, and this is our du dx. All right. That's the chain rule that we're doing right there. When we take the derivative of the right side, we simply get a 2, but we also get dy dx for the derivative of y. All right. Now we simplify, which gives me y e to the xy plus x e to the xy dy dx equal to dy dx. Right? We want to isolate the terms that have dy dx. It's very repetitive, same steps every time that I keep emphasizing. So isolate dy dx terms. Which gives me x e to the xy dy dx minus 2 dy dx equal negative y e to the xy. Then we want to isolate dy dx by factoring it out. And this gives us dy dx times x e to the xy minus 2 still equal to negative y e to the xy. Then we divide both sides by the coefficient of dy dx. Right? And we get a formula for the derivative. I'm not sure if Desmos can handle this one, but let's try it just to get a feel for what it looks like. E to the xy equal to y. Okay, and it handled it just fine. All right, it's kind of a weird looking thing. It sort of has the shape of an exponential, except that over here, instead of tilting outward forever, it's actually coming in towards the axis. So this is actually not a function because it doesn't pass the vertical line test on this section right here. But it is a curve. All right, if it's not a function, we just call it a curve, for lack of a better word. Okay, we have one left to do, which is to find the second derivative. Now, this means that once we take the derivative the first time, we're going to take the derivative again a second time. Okay, so first we take the derivative the first time. So we do this on both sides. Of sine x plus x squared y equal the derivative with respect to x of 10. All right, now the first derivative tells us about the tangent line. The second derivative tells us about the curvature of it, whether it's concave down or concave up, how it's curved. All right, so our first derivative is going to give us cosine of x. Then we have the product rule, plus 2xy plus dy dx times x squared equals 0. This is already sufficiently simple. I don't feel like I need to rewrite it. So I'm going to go ahead and isolate the dy dx terms. I only have one dy dx term. So I have x squared dy dx equal to negative cosine of x minus 2xy. Okay. Then I can factor out the dy dx and isolate it. And then the next step will be to divide both sides by the coefficient of my dy dx, which is x squared. So this gives me dy dx equal to negative cosine x minus 2xy, all divided by x squared. You cannot cancel the x because this x is inside the cosine, and as a part of the argument, it is never okay to cancel that out or factor it out. Never, right? I don't get to say never very often in mathematics. You may never cancel a variable or a factor inside of a trig function. You can't take it out, you can't cancel it. It stays.
I think you forgot an x in negative 2xy.
Oh, I did. Thank you.
Yeah,
Okay.
Just before it gets worse.
Yeah, yeah, you're right, because it will get a whole lot worse. One careless mistake and the whole thing will crash and burn. Okay, we're supposed to be finding the second derivative. So to find the second derivative, we want to take the derivative again. Remember that the second derivative is basically the derivative of the derivative. So when we take the derivative of the derivative, this gives us the second derivative of y with respect to x both times. So the placement of the 2 is between the d and the y and after the x. And it means the second derivative of y with respect to x both times. That's kind of the way it's interpreted. So we want to take the derivative of this part that's right here, which is going to be the derivative with respect to x of negative cosine of x minus 2xy, all divided by x squared. All right, you guys watch carefully and make sure I don't leave something off again, because that would be disastrous. All right, so our next step, once we have this, is we're going to apply the quotient rule. So the quotient rule, remember, is f prime g minus g prime f over g squared. So we're going to take the derivative of the numerator times the denominator minus derivative of the denominator times the numerator over the denominator squared. So this is going to give me derivative of a negative cosine will give me a double negative sine, which becomes positive sine. So I get sine of x minus, and then I've got to apply the product rule. So this time I may do minus 2x and y. So I've got a negative 2x. The derivative of negative 2x is a negative 2 times the y plus the derivative of y, which is dy dx, times negative 2x. And that's all the derivative of the numerator. So derivative of the first term gives me sine x. Derivative of the second term is product rule. And I thought of this as negative 2x times y. So I did the derivative of negative 2x, which is a negative 2 times y, plus the derivative of y is dy dx times the negative 2x. Right? My next thing to do, that's my f prime, is multiply all of this by g. So all of this gets multiplied by x squared. And we have a minus. And now I have the derivative of the denominator, which is 2x. And it gets multiplied by the numerator, which is negative cosine of x minus 2xy. And all of this gets divided by x squared squared. Now, x squared squared is x to the fourth. So we want to simplify this, and we want to distribute the x squared that is being multiplied by this factor here, and distribute the negative 2x being multiplied by this factor here and by in the parentheses. So distributing the x squared, I get x squared sine of x minus 2x squared y minus 2x cubed dy dx. And that takes care of the distribution of the x squared over the first factor. Now we distribute the negative 2x over the second factor. Negative 2x times negative cosine x is a positive 2x cosine of x. Negative 2x times a negative 2xy is a positive 4x squared y. And I'm dividing the whole thing by x to the fourth. Now you'll want to notice that I have two factors here that are alike, that are like terms. I have two x squared y terms. So because I have two x squared y terms, I'm going to combine those guys together. If I have negative 2 of them and I add 4, I end up with 2 of them. So now I'm going to start simplifying again. So I have x squared sine of x plus 2x squared y. And then I'm going to write plus 2x cosine of x. I'm going to do that one next. And the last thing I'm going to put on is the minus 2x cubed. Now, before I put in the dy dx, do I not know what dy dx is? Did I not have to find the first derivative before I could take the derivative again? So
Yeah, we know what it is.
Yeah, we know what it is. It's right here. It's minus cosine of x minus 2xy over x squared. So this is minus cosine of x minus 2xy over x squared. So we substitute the expression that we got for dy dx in place of the dy dx in the second derivative. And all of this is being divided by x to the fourth. Now we simplify again. So I have x squared sine of x plus 2x squared y plus 2x cosine of x. Now I've got x cubed times x squared. So the x cubed and x squared will reduce and I'll get a singleton x. So the x squared cancels 2 of the 3 and leaves me with 1x. So this gives me a minus 2x times a negative cosine of x, which gives me a plus 2x cosine of x. And then a negative 2x times negative 2xy gives me a plus 4x squared y, which gives me now additional terms that are like terms. Right? Make sure that you do the multiplication correctly. Right? And all of this is divided by x to the fourth. I have 2x cosine of x terms. and that gives me 4x cosine of x. So I have 1 x squared sine x term. I have 2 x squared y terms, so this becomes 6x squared y. And I have 2 x cosine of x, so I get 4x cosine of x, all divided by x to the 4th. Now, could I reduce it more? Yeah, I actually could. Every term in the numerator has an x factor that is not buried inside parentheses. So I could reduce it by 1x. So this would end up giving me x sine x plus 6xy plus 4 cosine of x, all divided by x cubed. Right? Now I'm at the point where nothing else can cancel. I can't do anything else. This is the best that the expression for the second derivative gets. And this, of course, will tell me about, about the concavity of the curve, right? Something about whether it's concave up or concave down at a particular point, right? Let's see, x squared y equals 2. All right, and here is what my graph looks like. It's kind of an interesting graph. It basically looks, well, it just sort of comes up. It's got a vertical asymptote, looks like here at the origin on the y-axis. So at x equals 0, and it approaches the x-axis, y equals 0, as it goes to infinity and negative infinity. Okay. All right. We're going to switch gears now, and we're going to talk about the derivatives of exponentials and the derivatives of natural logs. And then we're going to talk a little bit about logarithmic differentiation, which is, of course, related to implicit differentiation.